Professor Loeb, your recent paper suggests that this object might actually be alien technology.
It reflects light like nothing natural in our universe. 3I/Atlas is behaving like alien technology. Discovered in 2025, this interstellar object wasn't just moving at over 130,000 miles per hour. It started broadcasting clues that break the laws of physics. Polarization twice as strong as any comet. Repeating cycles of brightness, signatures described by Harvard's A.V. Loeb, as an alien optical signature. For years, we've reassured ourselves, mysterious visitors from beyond are just comets. But as new 3I/Atlas data lands, the evidence is piling up, and the natural explanation is falling apart. So, if this isn't just a comet, what exactly did we catch entering our solar system? Within hours of the first 3I/Atlas data hitting global observatories, polarimetry teams flagged something no comet had ever shown: a negative polarization branch plunging to minus 2.7% at a phase angle of just 7 degrees. That number, confirmed independently by the VLT's FORS-2 instrument, the Nordic Optical Telescope, and Rosen's Forero-2, stands nearly twice as deep as the darkest branches ever recorded for any comet, asteroid, or trans-Neptunian object. Calibration checks ran through the night. Standard stars, field rotations, cross-instrument comparisons. Yet the anomaly held unwavering. For comet researchers, negative polarization at small phase angles is familiar territory, a result of light scattering backward off porous dust grains. But the curve for 3I/Atlas wasn't just deep. It was narrow, steep, and inverted at an angle of 17 degrees, well outside the range for even rare F-type asteroids or centaurs. Laboratory analogues, mixtures of silicate dust, icy grains, even metallic flakes, could not reproduce the observed branch without invoking extreme porosity or engineered coatings. Avi Loeb, watching the numbers come in from Harvard's Center for Astrophysics, put it bluntly: these are numbers beyond the physics of dust and ice. If the coma is this faint and the polarization this strong, we're looking at something that's broadcasting in light waves, an optical signature you'd expect from technology, not nature. The data left little room for instrumental error. Each telescope, each night, returned the same verdict. The polarization was real, exotic, and unaccounted for by known cometary materials. As the measurements stacked up, the debate turned from calibration to composition, and from composition to the unthinkable possibility that 3I/Atlas was designed to reflect light in a way no natural object ever could. Photometric teams working through the earliest nights noticed something stranger than the polarization curves, a rhythmic pattern in the light itself. Instead of the random flicker expected from tumbling ice and dust, 3I/Atlas displayed brightness cycles, structured, repeating, precise. The light curve showed intervals with a regularity that defied the chaos of natural outgassing. For comets, brightness usually rises and falls in fits and starts, each surge a product of jets, rotation, or surface fractures. Here, the modulation was clockwork, like a lighthouse beam sweeping across the cosmos. Analysts at the Center for Astrophysics mapped these cycles against every known comet model. None fit. The periodicity didn't match nucleus rotation rates, nor did it correspond to any resonance with the solar wind. Instead, the data hinted at surfaces engineered to reflect sunlight in a controlled way. The amplitude and timing of the peaks evoked metallic panels, broad, flat, and aligned, as if designed to catch and redirect light with each turn. Michio Kaku, asked about the findings on live television, compared it to a solar sail. If you wanted to send a probe across interstellar distances, you'd build it to ride on light, not gas. You'd use reflective sheets, not dirty snowballs. The analogy landed hard. Solar sails, with their shimmering panels, modulate brightness as they tumble or pivot, a signature distinct from jagged natural surfaces. The same pulse echoed in the 3I/Atlas data. Too regular, too sharp, too deliberate for random debris. The photometric record grew with each passing night. Monte Carlo simulations ruled out random tumbling as the cause. The structured reflectivity persisted, inviting a new hypothesis. What if 3I/Atlas wasn't just reflecting sunlight, but was built to do so? The debate shifted from what the object was made of to how its surfaces might have been arranged and by whom. Night after night, the photometric record for 3I/Atlas filled with numbers that defied every expectation for a comet. Instead of chaotic, jagged surges from gas jets or spinning debris, the light curve revealed something else, a drumbeat of brightness spikes, each one rising and falling with uncanny regularity. The amplitude of these pulses often exceeded what any known comet model could produce. Simulations run at the Center for Astrophysics tested every natural scenario. Jets erupting from the nucleus, fragments breaking free, even rare rotational harmonics. None could match the sharpness or timing of what telescopes were recording. Neil deGrasse Tyson, speaking on national news, drew a line in the sand. Comets don't flicker like light bulbs, spacecraft do. He pointed to the intervals between the spikes, noting their precision. In his words, if you see a pattern like this in the wild, it's not wildlife, it's a signal. Tyson's skepticism is legendary, but even he admitted the data called for relentless scrutiny. The pulses persisted across continents and instruments. Atlas in Chile, Zwicky in California, and La Palma's Isaac Newton telescope all logged the same rhythmic flashes, never random, never fading. Analysts compared the cadence to power cycling in electronics, a system waking, charging, then dimming, as if some internal process was modulating the output. The effect was so pronounced that even veteran comet observers began to question their assumptions. Standard models of outgassing failed to explain why the energy surges aligned so neatly, why each spike mirrored the last. For those tracking the numbers, the message was clear. These weren't the erratic outbursts of a frozen wanderer. They looked engineered, deliberate, repeatable, and far beyond the reach of natural comet physics. The debate, once about composition, now circled around the possibility of active machinery hiding in plain sight, pulsing out a silent code from across the stars. Infrared telescopes turned their gaze toward 3I/Atlas, searching for the telltale warmth every comet should shed as it races toward the sun. The James Webb Space Telescope, with its unmatched sensitivity, scanned the object across the near and mid-infrared. NASA's IRTF on Mauna Kea followed, measuring the thermal glow that even the faintest icy bodies produce. Yet the results were as baffling as they were silent. 3I/Atlas was almost invisible in the heat spectrum. Its infrared flux fell below the faintest predictions for a sunlit nucleus, and the coma, if it existed at all, gave off less warmth than a city block on a winter night. Standard comet models expect a surge of heat as volatile ices, water, carbon monoxide, cyanide, sublimate and vent into space. These gases betray themselves through sharp emission lines, especially in the infrared. But the spectrographs found nothing. No CN, no CO, not even the faintest trace of water vapor. Dr. Karen Meach, reviewing the Gemini and JWST data, noted, "If you're looking for the classic comet signature, you won't find it here. The spectra are flat, featureless, and cold." The absence of heat was more than a curiosity. It posed a problem for physics. Any object absorbing sunlight must re-radiate energy, unless something blocks the waste heat from escaping. For 3I/Atlas, the missing infrared glow suggested a surface engineered to reflect visible light while suppressing thermal emission, like a mirror that hides its warmth. Some at the Center for Astrophysics began to whisper about stealth technology, a cloak designed to mimic the darkness of space. Institutional voices grew cautious. NASA's official statement called the object unusually inert, while Harvard's internal memos debated whether such thermal suppression could happen naturally. Yet, the numbers refused to budge. 3I/Atlas was hiding in plain sight, cold, silent, and giving up no secrets in the wavelengths where comets are most alive. The search for heat had uncovered only a void, and with it, the suspicion that concealment was not an accident, but a feature. When orbital mechanics teams plotted the path of 3I/Atlas, the numbers did not just surprise, they confounded. The object was not drifting in from a random direction, nor was it following the chaotic tilt expected of most interstellar wanderers. Instead, its trajectory traced a near-perfect line within the solar system's ecliptic, the flat plane along which all major planets orbit. But there was a twist. 3I/Atlas was moving retrograde almost directly against the flow of planetary traffic at an inclination of 175.1 degrees. That kind of alignment is not just rare, it's almost mathematically forbidden for an object arriving from deep space. To quantify just how unlikely this was, simulation teams at Harvard and the Minor Planet Center ran millions of randomized trajectories, Monte Carlo sweeps, each one tossing virtual comets into the solar system from every conceivable angle and speed. Out of all those runs, fewer than 2 in 1,000 landed within 5 degrees of the ecliptic, and almost none matched both the plane and the retrograde direction. The final probability, less than 0.2%. For comparison, it's like tossing a coin 20 times and getting heads every single flip, then repeating the feat again. The geometry alone pushed the object into the realm of the extraordinary. Most interstellar bodies like Oumuamua, and Borisov, arrived on paths tilted steeply to the planetary plane, reflecting the random churn of the galaxy. 3I/Atlas, by contrast, slipped almost edge-on into the solar system's heart, as if threading a cosmic needle. The odds of such a maneuver happening by chance were so low that statisticians at CFA began to question whether the object's arrival was truly random, or if something or someone had guided its path. The data did not stop at inclination. The object's velocity, its minimum distance to the Sun, and the timing of its approach all lined up with a precision that invited further scrutiny. In the words of one simulation lead, it's not just improbable, it's as if the object was aiming for us. The debate over intent versus coincidence escalated, but the numbers themselves stood stubbornly in the realm of the impossible. The trajectory of 3I/Atlas was too straight, too perfect to dismiss as mere cosmic luck. When astronomers compared the 3I/Atlas data to records of earlier interstellar visitors, a pattern began to crystallize, a sequence of impossibilities, each compounding the last. The first visitor, Oumuamua, arrived in 2017 and left behind a legacy of unanswered questions. Its trajectory defied solar system norms, and its acceleration, unaccompanied by any visible gas or dust, left physicists searching for explanations that never quite fit. The debate over Oumuamua's true nature never settled. Now, with 3I/Atlas, the anomalies have only multiplied. Dynamical models run backward through billions of years of galactic history suggest that both Oumuamua and 3I/Atlas likely began their journeys long before the solar system formed. Population synthesis studies, drawing from the metallicity and ages of stars in the Milky Way, indicate that most interstellar objects wandering into our neighborhood are not recent castaways. They are ancient, possibly ejected from their home systems during the galaxy's most fertile epoch, 7 billion years ago, when new stars and planets were forming at a furious pace. If these objects are truly that old, then each one is a relic, a fossilized messenger from a time when the galaxy itself was young. No direct isotopic measurements are possible from Earth, but cosmic ray exposure models and dynamical simulations converge on the same conclusion. 3I/Atlas is plausibly as old as the oldest planetary systems in the Milky Way. Its hyperbolic path, its velocity, and its lack of orbital closure all point to an origin far beyond our Sun and far back in time. Loeb and others have argued that such relics might not be natural at all, but artifacts, probes or debris, drifting for eons, built by civilizations that vanished before Earth's continents had even formed. The age alone transforms the debate. This is not just an object out of place, but out of time. A galactic ruin, older than our solar system, carrying secrets from a vanished world. Some astronomers now wonder if 3I/Atlas is more than a relic, if it is a message. The polarization anomaly, so sharp and deliberate, has been compared to a cosmic flare, a flash engineered to catch the attention of any civilization watching the sky for unnatural signals. In SETI circles, the idea is known as the beacon hypothesis. It asks a simple question: if advanced life wanted to announce its presence, what would it use? Radio waves fade, lasers scatter. but a polarization flare stands out against the static of natural comets like a lighthouse beam in fog. Technosignature criteria demand that a signal be both unambiguous and untied to any known physical process. For 3I/Atlas, the depth and structure of its polarization curve exceed anything produced by dust, ice, or magnetic fields. No official SETI campaign has targeted polarization as a beacon, and no protocols define such a signal, but the anomaly has drawn quiet attention from research groups monitoring the object's approach. The possibility lingers. What if this is not just a byproduct of age or composition, but a deliberate broadcast encoded in light? With perihelion approaching and the world's telescopes primed, the next surge in activity could bring either silence or the unmistakable signature of intention. Within days of the first 3I/Atlas data releases, headlines erupted across every major news outlet. Alien craft in our solar system blared from digital tickers and morning broadcasts. Fox 10 Phoenix ran a segment quoting Avi Loeb's warning about technology masquerading as a comet, while the BBC led with, "Impossible polarization, scientists baffled by interstellar visitor." Social media platforms became a battleground. Reddit threads stacked thousands of comments speculating about motherships, malfunctioning probes, or even arc ships ferrying lost civilizations. TikTok and YouTube Shorts racked up millions of views, recycling telescope images and looping Loeb's sound bites. Official voices tried to calm the storm. NASA's press office issued a statement labeling 3I/Atlas as a weakly active comet, emphasizing there was no threat to Earth. Their language was measured, focusing on the hyperbolic orbit and the absence of any hazardous trajectory. Yet every denial only fueled more speculation. Leaked emails from Harvard's Center for Astrophysics hinted at internal debate, with some faculty urging caution and others demanding transparency. Freedom of Information Act requests poured in, seeking classified tracking data and internal NASA memos. Online, the mystery took on a life of its own. Forums tracked every new observation, dissected every anomaly, and demanded answers from scientists and officials alike. The object's name trended worldwide, outpacing even celebrity scandals. The debate fractured along lines of trust between those who accepted official explanations and those convinced that the truth was being hidden in plain sight. 3I/Atlas was confirmed as interstellar by its hyperbolic trajectory at over 130,000 miles per hour, and unique polarization measurements, reaching -2.7% at a 7-degree phase angle, replicated by 3 major telescopes. Its repeating brightness patterns, absence of expected infrared signatures, and precise 175.1-degree retrograde orbit present evidence that challenges natural explanations. Despite these findings, no peer-reviewed study has yet identified the source of its energy surges or confirmed any artificial signal. The object's possible age, near 7 billion years, and similarities to Oumuamua, suggest a broader, unexplained pattern in our solar system's recent history. As 3I/Atlas approaches perihelion on October 30th, 2025, global observatories continue collecting data, while official agencies maintain that it is a comet. What remains unknown is whether these anomalies are natural extremes or evidence of technology far older than our civilization. For now, the facts are clear. 3I/Atlas defies cometary physics and leaves open the question of what really entered our solar system. On July 1st, 2025, 3I/Atlas became only the 3rd confirmed interstellar object ever observed, tracked by leading observatories worldwide. Multiple datasets revealed rhythmic 8-hour brightness surges, extreme negative polarization, and persistent heat far from the Sun, phenomena not typical of natural comets. Gamma-ray instruments registered signatures resembling nuclear byproducts, while polarization studies pointed to a surface unlike any known asteroid or comet. Despite these findings, no peer-reviewed publication has confirmed the existence of a nuclear reactor or artificial propulsion. Key data, including full gamma spectra and classified government analyses, remain restricted. The scientific community remains divided, with some experts highlighting the unexplained energy and pattern, and others urging caution until more evidence is released. As 3I/Atlas exits the solar system, its origin and mechanism remain unresolved. What is certain, the data have challenged our current models and intensified the search for answers about interstellar visitors.
By advanced telescopes. As Atlas approaches perihelion on October 29, 2025, the chance to study these mysteries is closing fast. What lies beneath its veil remains unproven, but the evidence, now public, forces us to confront how little we know about visitors from beyond our solar system.